There are 400 billion suns in the Milky Way, surrounded by trillions of planets. Mathematically, our galaxy should be teeming with alien empires. Yet, when we look out into the cosmos, we see absolutely nothing. In 1950, physicist Enrico Fermi distilled this glaring mathematical contradiction into a single, straightforward question: where is everybody? He posed this over lunch with colleagues at the Los Alamos laboratory. They were discussing the sheer scale of the universe and how statistically easy it should be to spot neighboring civilizations. A single advanced civilization could send out von Neumann machines, artificial intelligence probes designed to mine materials, build copies of themselves, and spread. Using these self-replicating probes, a species could map the entire Milky Way in a few tens of millions of years. While tens of millions of years sounds like a vast span, the universe is over 13 billion years old. There has been more than enough time for multiple empires to rise and spread across the stars. We see no massive megastructures. We hear no radio signals. This silence suggests a universal barrier actively prevents intelligent life from filling the cosmos. The rare Earth hypothesis suggests that while basic microbial life may be common, the evolution of complex, multicellular animals requires a precise set of astronomical and geological parameters. Earth may have won a near-impossible cosmic lottery. This analysis of cosmic dead zones shows that regions like globular clusters or the centers of galaxies are too heavily irradiated or metal-poor to support complex life. Even in a safe neighborhood, you need the right planetary siblings. A massive gas giant like Jupiter is required to act as a gravitational shield, clearing out comets and asteroids that would otherwise collide with a young planet. This geological research identifies plate tectonics as a requirement for complex life. Without the slow movement and recycling of the planetary crust, a planet cannot regulate its global temperatures or maintain a stable biosphere. We also rely on a large moon. Its gravitational pull stabilizes Earth's tilt, ensuring the climate stability necessary for life to evolve over billions of years. Earth survived a perilous chronological obstacle course. The lack of aliens in our night sky might simply be because complex life is a statistical anomaly. But if complex life does form on other worlds, it may eventually hit the Great Filter. This theory argues that civilizations inevitably hit a universal choke point that prevents them from becoming spacefaring empires. Physicist Brian Cox argues that the industrialization required for spaceflight forces a species to master the same physics required for total self-annihilation. During this brief industrial window, civilizations face self-imposed threats. They extract resources, irreversibly altering their planet's climate, and they develop nuclear weapons capable of erasing their entire species. Economist Robin Hanson outlined 9 evolutionary steps toward a galactic empire. The Great Filter might lie right at the final step, the transition from a regional civilization to a colonization explosion. This creates a statistical problem known as transient detectability. If civilizations routinely destroy themselves shortly after industrializing, their brief windows of existence rarely overlap. They flare up and burn out before we ever see them. If technological civilizations routinely collapse, the Great Filter remains an imminent threshold in our immediate future. There is an alternative. What if super-civilizations do survive, but they intentionally remain hidden? The Kardashev scale assumes an advanced race would build massive, energy-guzzling megastructures like Dyson spheres to harness the power of stars. But that assumption might be a projection of our own industrial infancy. A newer hypothesis proposes technological minimalism. It argues that a truly advanced intelligence would master engineering at the quantum scale rather than the astronomical scale. Extreme miniaturization would allow for perfect energy efficiency. A civilization could operate in closed-loop systems that leave zero ecological or thermal footprint, making their homeworld appear untouched to our telescopes. Moving matter across light years requires immense energy expenditure that cannot be bypassed by efficiency alone. This makes the energetic signatures of interstellar travel the most promising target for our search. The galaxy might actually be populated, but because advanced intellects optimize their existence rather than violently expand, They remain indistinguishable from the background radiation of the cosmos. The Fermi paradox acts as a mirror, reflecting humanity's own precarious timeline and expansionist history. If the rare Earth hypothesis is correct, and the galaxy is mostly dead, we are the sole custodians of consciousness in this quadrant of the universe. This realization has given rise to astroethics, a field that examines the ethical considerations of our potential contact with life and our responsibility to respect other beings. Carl Sagan suggested that to survive the Great Filter and reach the stars, a civilization must first solve its predatory and violent impulses. We face a final human dilemma. We must choose to evolve past our primitive impulses and master the elegance of restraint. If we fail, we will inevitably fall to the filter. The universe's silence asks, are we the first to survive the gauntlet, the next to fall, or the only ones here to speak?